Hello everybody, welcome back to Physics 425. What we've been talking about recently is some quantum mechanics review, which allowed us to write down wave functions for identical particles and deduce the Pauli exclusion principle for systems of fermions, identical fermions. And then we use that to understand some concepts like the Fermi energy and the density of states. And in the last video, we calculated the low temperature heat capacity of a system of identical fermions. Today, what we'll start with is writing down an expression for the low temperature entropy. And that will be really quick. And after doing that, we'll start to think about mixtures of the two isotopes of helium. Helium-3, which is a fermion, and helium-4, which is a boson. That will require some discussion of chemical potential, and we'll start to think about the energetics of these mixtures. Okay, and so let's just review the results from last time. The main result was that at low temperatures, the system of identical fermions has a heat capacity that is proportional to temperature. So we want to use that to calculate entropy. And let's start by remembering the relationship between heat and entropy. dq is T ds. And then let's divide by a small temperature interval such that dq dt, which we can identify as the heat capacity, and let's imagine we're doing this at constant volume, is going to be equal to T, and then it would be ds dt at constant volume. So let's rearrange and let's see if we can write down an expression for entropy. What we would do is we'd first divide by T and then integrate with respect to temperature. S is going to be the integral with respect to temperature of the heat capacity divided by T, and that integral is over temperature. Okay, but our heat capacity is proportional to temperature, so when we divide by T, we just get a bunch of constants, and those constants, if you remember, are pi squared over 2, then there's an nkb, and then we had T over the Fermi temperature, so we just have 1 over the Fermi temperature now. And then we have a dt. So that if we were to now evaluate the integral, we just have the integral of a constant, and we would get S is equal to, in fact, it's the exact same expression that we had for the heat capacity. And so the low temperature entropy and heat capacity are the same expressions. Okay, good. So that was just tidying up one little detail that remained from the last discussion. So really the focus of today's video is on thinking about helium-3 and helium-4 mixtures. And let's just recall some of the things that we already have established. We already established that helium-3 and 4 are electrically identical. They have the same number of protons and the same electron configuration. The only difference is the number of neutrons in the nucleus. What we had found is that helium-3 had a larger zero-point energy. And that was really a consequence of the lower mass of the helium-3 atom because it has one less neutron. And so this zero-point energy we deduced was proportional to 1 over the mass. And so what that really means is that at zero temperature, the helium-3 atoms have more kinetic energy, And so if you can imagine, they're kind of vibrating around with more vigor than the helium-4 atoms, and that means they take up more space. So they have more kinetic energy, and they take up more space per particle. And that idea is going to be important for what we're going to discuss today. Just as a way to verify that concept, if we write down the density of liquid helium-3, it's 0.082 grams per centimeter cubed, and for helium-4, it's 0.1451. So it's almost a factor of 2, not quite, but the helium-3 is less dense because each of the individual atoms takes up more space. And then the latent heat is the heat required to convert the liquid into a vapor. And helium-3 already has a bunch of kinetic energy because of the high 0-point energy, and so it takes less energy to vaporize liquid helium-3 than it does liquid helium-4. Okay, the other important difference is that helium-3 is a fermion. And probably not for today, but we will eventually make use of the fact that its Fermi energy is what we calculated last time for a three-dimensional system, h bar squared over 2m, 3 pi squared n L cubed, or the volume, alternatively, all to the 2/3 power. So those are the basic things that we know. Okay, so now let's think about what we mean by chemical potential. And so that will be the symbol mu. So if we just write down the first law of thermodynamics, we've used it a lot. It's just that the change in internal energy is dq or TdS minus P dV, which is the work. When we write it in this way, this law implicitly assumes that the number of particles in whatever system we're thinking about is fixed. And so that's often a good assumption if you had a gas in a closed container or something like that. But what if we had a system with a variable number of particles? Okay, an open jar or something like that. Then, well, you could certainly imagine as our system loses or gains particles, then its internal energy would be changing. And so maybe we have to generalize this first law. For an example of a fixed number of particles in a system, you can think of one electron in a hydrogen atom. So we have one particle distributed among the many atomic energy levels of the H atom. And so that's an example of thinking of a system with a fixed number of particles. However, we could think of the system in a different way. We could choose a different system. What if our system was just one of the atomic energy levels? So, however, if we take a single energy level of the H atom, whichever one you want, like the n equals 3 energy level. And we could look at that and we could say, well, either that level has the electron or it doesn't. And so the occupancy of that level is either no particles or the 1 electron. And so in this view, the particle number in our system, the one state of the hydrogen atom, is variable. Okay, so if we add or remove particles from the system, then we would clearly expect the internal energy of our system to change. Okay, so previously we had written the internal energy, or the change in internal energy, du is TdS minus PdV, and so our internal energy was a function of the entropy and volume. But now what we're going to do is we're going to add particle number. And so in that case, if we take a differential of the internal energy, we're going to get du ds, keeping the volume and n constant, plus du dv, keeping entropy and n constant. And now we're going to get a new term. It's du dn, keeping s and the volume constant. This first partial derivative is temperature, so that we get the TdS. The second partial derivative is minus the pressure, so we get minus PdV. And we'll identify this third partial derivative as the chemical potential. And so this is going to be chemical potential. And I think I'm going to call this equation star. Okay. And so written in terms of these variables, then we have that du is equal to TdS minus PdV plus mu dn. And what we have here is, this is the heat, dq is TdS. This is the mechanical work, so a change in the physical size of the system, and this is going to be identified as chemical work, change in energy due to a change in particle number. And so we could write this then as dq minus dw, where the net work includes both the mechanical and the chemical work. In order for this expression to be dimensionally correct, like du is obviously a change in energy, dn is just a number of particles, it doesn't have any units, and so it must be that this chemical potential has units of energy. And this mu dn term is the energy increase of the system when we add dn particles. Right, and so if dn was negative, then mu dn would be negative as well. Okay, so let's go back and let's just look at this equation star here, and let's see if we can solve for the chemical potential. Well, if we kept the internal energy constant and the volume constant, then we would have what? We would have du ds, which is T. Well, in fact, actually we should look at this equation. So let's imagine U is constant, so du goes away, and V is constant, so V goes away, and we could solve for mu. We would get 0 is equal to T ds plus mu dn, and so this is at constant U and V, and so therefore mu would be equal to minus T ds dn at constant internal energy and volume. Okay, good. So there's some interpretation of chemical potential. So let's see if we can start with some kind of qualitative understanding of mixtures of helium-3 and helium-4. So here's the scenario. We imagine that we have two containers. One is pure liquid helium-3, and the other container has pure liquid helium-4. And this is at T equals 0, or really low temperatures. Okay, so here we have, here's the helium-4 container, and here's the helium-3 container. What we'd like to do is we'd like to add one helium-3 particle. And the question is it energetically favorable to add that one helium-3 atom to the liquid helium-4 or the liquid helium-3 container? So we want to add one helium-3 particle. Is it energetically favorable to add it to the liquid helium-3 or liquid helium-4? Another way of asking this question is to say, is the helium-3 atom that we're going to add, is it more strongly bound inside the liquid helium-4 or inside the liquid helium-3? Okay, so we make the following note. Because helium-4 has the lower 0 point energy, it is more dense. And so that's a point that we actually already made near the beginning. So therefore, if we add the helium-3 atom to this liquid helium-4, it will be closer to the neighboring helium-4 atoms compared to if it was added to the liquid helium-3. Helium atoms interact with one another. There's an attraction due to the van der Waals force, and that van der Waals force gets stronger if the distance between neighboring atoms is small. And so this tells us then that we expect the van der Waals attraction between the helium-3 that we added to the liquid helium-4 to be relatively strong because it's close to its neighbors. So this attraction, due to the van der Waals force, between helium-3 and the surrounding helium-4 is relatively strong. Okay, so in contrast, if we add the helium-3 atom to liquid helium-3, its neighbors are farther away because it has a higher 0-point energy, and therefore each atom occupies more space. And the van der Waals attraction is weaker. I think we can try to kind of sketch the idea. And so let's start with a helium-3 atom in liquid helium-4. So let's suppose that this is our helium-3 atom. And so this little bubble represents the volume occupied by a helium-3 atom. And then surrounding that are the helium-4 atoms, and they occupy less volume because they have the lower 0-point energy. And so all these little bubbles represent the space occupied by helium-4 atoms. Okay, and so this is the volume occupied by helium-4 atoms. Okay, and so what we can do is we can kind of come up with a characteristic distance between a helium-3 atom and a helium-4 atom, between its neighbor. And so this is the typical distance between the helium-3 atom and its neighboring helium-4 atoms. And that distance is on the small side because the helium-4 atoms occupy a relatively small space. If we draw a similar picture for helium-3, a single helium-3 atom added to liquid helium-3, you could probably picture what it's going to look like. This is our helium-3 atom, so let's say this is the one added helium-3 atom. And then it has a bunch of neighbors, and those neighbors are also helium-3 atoms. So they have these bubbles that are about the same size, and so it's all these big, large bubbles. And when we draw this distance, this is a relatively large distance. Large distance between neighboring helium-3 atoms. Okay, and so really this is a quantum mechanical argument because the 0-point energy, what we ended up doing was deriving that, or making at least the argument based on the Heisenberg uncertainty principle. Okay, so in liquid for helium, the average distance between the helium-3 atom and neighboring helium-4 atoms is small. And not only that, not only is that distance small, there's actually more neighbors. There are more neighbors to interact with. And if there's more neighbors to interact with, there's more strong binding due to the van der Waals force. So since the helium-3 and helium-4 atoms are electrically identical, the attraction between helium-3 and helium-4 and helium-3 and helium-3 is determined by the same van der Waals force. So the conclusion is that helium-3 is more strongly bound in helium-4 because there's more neighbors with shorter distances. Okay, and so the original question is it energetically favorable to add this helium-3 to the liquid helium-4 or the liquid helium-3? The answer is it's energetically favorable to add it to the liquid helium-4. Okay, so let's connect this with chemical potential then. And so we'll start by thinking about one helium-3 atom in liquid helium-3. So this is not the energetically favorable scenario, but let's start with this one. So the energy to remove one helium-3 atom from the liquid, in other words, the binding energy, is, by definition, determined from the latent heat. The latent heat of evaporation. Okay, so this chemical potential then, and so the notation here with the subscript helium-3 is the chemical potential for a helium-3 atom in liquid helium-3. Is minus the following notation. So I'll define what I mean by this. So L sub 3 is the energy of N0 plus 1 liquid helium-3 atoms, which is lower than the energy of N0 liquid helium-3 atoms plus 1 free helium-3 atom. So actually what I really should be doing is, this note refers to the negative sign. So if we had N plus 1 helium-3 atoms, and we put N of them into the liquid and then had just one isolated, that's a higher total energy than having all N plus 1 as part of the liquid. And the reason it's a higher energy is because when we add that atom into the liquid, there's a binding energy that lowers the total system energy. Okay, this 0 means we're talking about the 0 temperature limit. Okay, good. So the latent heat obviously defines how strongly bound helium-3 is in liquid helium-3. So now let's start to think about one helium-3 atom in liquid helium-4. Okay, so the binding energy of a single helium-3 atom in liquid helium-4 is, let's call that epsilon. And what we'll do is we'll say that our chemical potential is therefore minus epsilon. So this now is the chemical potential for a single helium-3 atom in liquid helium-4. Okay, so because of the lower 0 point energy of helium-3, the helium-3 atom is more strongly bound when it's in the liquid helium-4, which means that the chemical potential in the case of helium-3 and liquid helium-3 is greater than it is in liquid helium-4. And so what we could do is we could draw a picture here. And so here's this axis is chemical potential, and over here is going to be 0. Oops, sorry. 0. Now the chemical potential for the helium-4 case is minus epsilon. And so we'll put that over here somewhere. And so this is mu helium-3 atom in liquid helium-4 is minus epsilon. And then over here is the case for helium-3 atom in liquid helium-3, and that's minus the latent heat divided by N. And so we have minus the latent heat divided by N. And so that's what it is for a single particle. And then what we're going to imagine doing is, what if we keep adding helium-3 atoms one at a time? So if we start with liquid helium-3 and then we keep adding helium-3 atoms, then we just keep making more and more liquid helium-3. And so the latent heat doesn't change because we change the volume of liquid helium-3. And so this is just going to stay constant. And what we're going to imagine is this horizontal axis is x. So this is going to be the helium-3 concentration, that's not going to fit. Here, let me try again. This is X, and this is going to be the helium-3 concentration in liquid helium-4. And so what we want to know is, does this chemical potential mu4 helium, does it change as we keep adding helium-3 atoms to liquid helium-4? And if it does change, how does it change? And so that's the question for next time. So how do the energetics of helium-3 in liquid helium-4 change as the concentration X increases? So we won't be talking about just a single atom. What if we have a collection of atoms? Okay, and so that's the question we'll try to answer next time. And I will see you then. Thank you.